Good afternoon. My name is Ross Virginia. I'm a member of the Environmental Studies Program faculty, and it's also my pleasure to direct the Institute of Arctic Studies, which is a unit of the Dickey Center for International Understanding. It's a real pleasure to welcome you all to this special seminar today. The Dickey Center and its Institute of Arctic Studies have identified climate change and its impact on northern peoples and northern environments, and also the polar regions more generally, as an area of special focus. This term, the Institute launched a brand new program called IGERT. This is a 5-year NSF-funded training program to really build the next generation of polar scientists and engineers and scientists who have an appreciation for the human dimensions of climate change and are able to connect science to policy and to the needs of people. As a kickoff for this new graduate program, the acronym for this is IGERT, and there are some brochures out in the back, the commercial, if you want to find out more about IGERT, or visit igert.org to find out what we're up to. As a kickoff for IGERT, we've begun a brand new seminar series, which will continue throughout the year. And the title of this is Dialogues in Polar Science and Society. The series will feature distinguished scientists, social scientists, policymakers, and leaders, indigenous leaders from the North, to talk about the pressing issues facing a rapidly changing polar environment. I can't think of a better person to kick off this new series, this new dialogue in polar science and society, than Lonnie Thompson, distinguished university professor in the School of Earth Sciences and a research scientist at the Byrd Polar Research Center at The Ohio State University. You can't pick up a newspaper these days, a magazine, without finding some article about the accelerating rate of melt, the loss of ice and snow on the planet, the rapid change in what we call the cryosphere. The public image of climate change has now become what? It's the polar bear on the melting piece of ice teetering in the Arctic Ocean. That really is the face of climate change. This is an exciting event. This is sort of exciting if you're a polar scientist, this attention. But it wasn't always this way. We're a fairly small community of scientists, and we worked for decades really largely out of public sight and certainly out of the sight of policymakers. But what has changed? What's changed today? Well, I think in part it's due to the pioneering and visionary work of a small number of very creative and dedicated scientists who have taken the challenge of trying to read the ice and find the climate story embedded in the ice, share that story with the world, and share with us the urgency of taking action on controlling the Earth's, at least moderating, taking charge of the Earth's climate system in order to achieve a more sustainable future. Our speaker today is Lonnie Thompson. Timing is everything. Lonnie began his graduate work in earth sciences at Ohio State just as the first deep ice cores were being recovered from Greenland, and he had the opportunity to begin to work on that ice. This got Lonnie interested in ice, but he decided perhaps I needed a slightly different road, a different approach to this. He realized that people don't live on ice sheets, that about 50% of the Earth is located in the tropics, and most of the Earth's population is found there. So Lonnie decided, why not study tropical ice? There is ice in the tropics, but it's located at the top of the very high peaks in the tropical regions. So Lonnie has developed his career around recovering ice from these remote regions to help us understand global climate change and the connection between the tropics and the Arctic and Antarctic systems. This approach sounds easy, but in fact, it is a tremendous challenge. It requires getting people, drilling equipment, scientific equipment, in and out of very remote, dangerous regions at high elevations. And Lonnie is the pioneer. He's the person that figured out how to do this and is still the very best at doing it. And Lonnie pioneered the way to get people to these peaks and has established this mountain glaciology as an important part of climate science. In this process, he's had a major influence on climate policy by communicating science to important leaders around climate change. If you've seen Inconvenient Truth, much of the climate science in there is around some of the things that Lonnie has done, and Lonnie has helped improve the science in the way it's presented to the public. Al Gore says, in speaking of Lonnie, no scientist has taken bigger risks to track ancient weather patterns and help us understand the anomaly of current climate trends. So what has Lonnie learned? What is he sharing with the world and the scientific community? His observations of glacier retreat over the past 3 decades confirm that glaciers around the world are melting. And he provides clear evidence that the warming of the last 50 years is now outside the range of climate variability that we've seen over the last several thousands of years. This is very important to separate these drivers in this pattern of climate change. Much of the work that Lonnie has accomplished, he's done in association with his wife, Ellen Mosley Thompson. Ellen is the director of the Byrd Polar Research Center at The Ohio State and an internationally renowned paleoclimatologist in her own right. I think the two of them together sort of define the meaning of a busy relationship. Lonnie, throughout his work, has been recognized with many, many different honors, and many of these are also shared with Ellen. 2005 seemed to be a particularly good year for Lonnie, and he nodded a little bit. He was elected by his peers to the National Academy of Sciences. The one I like best, he was coined the ice hunter by an article in Rolling Stone magazine, which, in recounting his science, made the statement that no other person has spent more time above 18,000 feet than Lonnie. Okay. Remember that number, 18,000. At lunch today, I've learned that he's actually accumulated more than 4 years of time above this elevation in the pursuit of his science. A truly remarkable feat physically, and when you think of working and getting science out of that environment, truly amazing. In that year, he also won the Tyler Prize for Environmental Achievement. In the environmental science community, this is our Nobel Prize. This is among the highest international recognitions for environmental science. Shortly thereafter, in 2007, Lonnie was awarded the National Medal of Science, which is this nation's highest honor for scientific endeavors. Lonnie is not resting on his laurels. I found a quote in 2009 in Nature Reports that this year that Lonnie has now spent more time above 20,000 feet than any other human being. Now that's a gain of 2,000 feet since the 2005 article in Rolling Stone. So Lonnie just keeps climbing higher, searching for the ice. I think that really describes his approach to the world. The title of his presentation today is Global Climate Change, a Paleoclimate Perspective from the World's Highest Mountains. Please join me in a very warm welcome for Dr. Lonnie Thompson.
Thank you, Ross. Appreciate that. It's my pleasure to be able to speak here at Dartmouth College today. I appreciate all that you said, but what I really do is what I love to do. And if you find that in life, you're very fortunate because you get recognized, but it's really loving what you do that's so important. I always tell my students I went to university to find a career, but along the way I found a purpose. And so I think that's what we need to find. But I want to talk about glaciers and what's happening to glaciers around the world, and particularly in the tropics. And there are wonderful places, as you can see here, Huascarán down in the Andes of Peru. This is the world's highest tropical mountain. I want to give full credit to a team of people in our group that work day and night on this subject. And if you look at the names, you'll see that they're international. There's no way that we could do what we have done without this international collaboration. And of course, you need funding agents to fund that research. And we've been very fortunate over the last 33 years to have both. So there are a number of topics I want to discuss. One is the evidence for climatological uniformity and amplification at high elevations in the tropics of climate change. Evidence for recent acceleration in the rate of ice loss in the tropics, and I'll give 3 examples. The Calcaya ice cap in the Andes of Peru, Nanunami over in the Himalayas, in Kilimanjaro in Africa. Impacts on past civilizations. If you recover records of climate in places where cultures have developed, you can also look at how past cultures have reacted to climate change. And I want to look particularly at an abrupt climate change occurring in a warm period, 5,000 to 5.5 thousand years ago. And a clear and present danger that in the last few expeditions that many of these glaciers are actually now being decapitated. They're no longer accumulating snow at their highest elevations. Therefore, they're starting to lose mass from the top down. And that has important implications for water supplies for people who live in these areas. Then finally, I'll talk about a few conclusions. If we talk about climate of the Earth, we know that there are many natural mechanisms that have been at work for thousands of years. Changes in the sunspot cycle, 11, 12-year cycle, the Gleisberg cycle, 90 years, affects the amount of energy coming to our planet. Changes in the amount of volcanic dust in the atmosphere, both the tephra and the sulfates. This is the eruption of Pinatubo in 1991 that cooled the world's temperatures for 2 years after the eruption. And there's internal variability in our climate system. INSO is an excellent example of this, the monsoon systems. These are natural variations that have occurred at least over the last 5,000 years where we have records of them. And then there are the human factors that have come into play more recently. The changes in the concentration of greenhouse gases. That continues to rise, and I'll talk a little more about that. Changes in aerosols and particles from the burning of fossil fuels, sulfate particles, soot. This is a fire in Guatemala back during the 1998 El Nino, and you can see the smoke coming into the central part of the U.S. And then there's changes in reflectivity of the Earth as we clear forests for croplands and various purposes, and the fact that we have 6.7, now 6.8 billion people living on the planet, this continues. And these are all the different ways that we as humans can change the climate of the planet. The Earth is getting warmer. We know that from many, many different records. One is which is our temperature records. And if you look at this record, the warmest year to date is 2005. And over the last 100 years, temperatures have risen about 0.75 degrees C. And in today's world, we have a good idea of where those temperature changes are taking place. We can look at it globally, and you can see those temperatures rising faster up in the Arctic and down in the Antarctic Peninsula, but also in the interior of many of the large continents around the Earth. So these are changes that are well documented, not only in the meteorological records, but in a lot of the paleo records that we look at around the world. The longest record we have of greenhouse gases measured in ice comes from the Epica cores from East Antarctica. And these records now go back over 800,000 years. And the blue curve here shows the CO2 variations. The red is methane. And you can see that ranges from about 180, 190 parts per million at the height of an ice age, when there's a lot of ice on the planet, to about 300 parts per million by volume max. Today, we're at 387 parts per million by volume for CO2. And if you look at that, you can see that there's no analog in that history compared to the day's record. But the real concern is where we're headed. And there are various scenarios of where we'll be in less than 100 years. And this is a scenario where we actually do something about emissions of greenhouse gases to our atmosphere. And of these, the most concern is CO2 because of its mean lifespan, which is 70 to 120 years. And we now know that actually 20% of the CO2 we're emitting today will be affecting the climate of this planet 1,000 years from now, because there's a long tail on the way CO2 goes back into the system. So these are things that we're very concerned about. And if we look at what we know about temperatures of the planet for the last 1,000 years, we have many different records. They're shown here. But you can see where we are now. These are in the actual temperature measurements. And where we are projected to be by the best models that we have to study climate. Models aren't perfect, but we're already here. And where we end up on this projected curve by 2100 really depends on what the energy policies are for the planet by that time. But if you take the mean of this projection, a 3 degrees C warming, we're talking about temperatures that we haven't seen since the Pliocene, which is about 3 million years ago. And then if you ask what was sea level 3 million years ago, our best records suggested somewhere between 10 and 25 meters higher than today. And those type of sea level changes would have tremendous impacts on our planet. They would change the geography of our planet. So these are some of the concerns. Now, there's been a lot of discussion on climate change issues, lots of reports, but it's very important to understand if you look at the actual emissions of CO2, they continue to rise. These are the timing for all the IPCC, Intergovernmental Panel on Climate Change reports, but the CO2 emissions from fossil fuel burning and cement manufacturing continue to rise. And so even though this is highly discussed, we are not really doing a lot about this issue. If you look at the Earth at night, you've all seen this photo. In today's world, about 88% of the energy, our energy consumption, comes from fossil fuels. And it's interesting to look at where General Electric projects this picture would look like by 2030. And this is what they think the planet would look like. If we're still looking at the same carbon-based energy, we'll lose most of the glaciers on this planet. Now you can look at this and you can think, well, this is very discouraging, but there's also an opportunity here. We know that 80% of the light that we produce at night to light the streets is actually going into space for no purpose. If you were to redirect that, you could make tremendous changes. So to me, it's a matter of when are we going to get serious about actually doing something about energy consumption and particularly CO2 emissions to the Earth's atmosphere. Well, there are many recorders on our planet of climate, and they all contribute to understanding how the climate has worked in the past. And I've listed some of them here. The one we're concerned with is the ice core records. And they come from around the world now. And they can give you very long histories, like that 800,000-year history from East Antarctica. But we also now have some fairly high resolution records and records going back 25, 30,000 years in the tropics. And this actually is the margin of the Quelccaya ice cap, which was the first tropical ice cap drilled. And this was taken back when I was a graduate student. And it shows those very distinct annual layers. Each one of those is a year. It's a very distinct wet and dry season. And I've been able to go back to this ice cap long enough to see the changes. This is the 1977. This is what the same place looks like in 2002. And it kind of brings home the message here that not only are we losing the history in the ice as they melt, but we're also losing a very important water resource for the people who live in these areas. Ice cores are remarkable recorders of many things in the environment. And I think what makes them special is that they record not just climate, things like temperature through the stable isotopes of oxygen and deuterium. They also record precipitation, net balance, the thickness of those layers. But they also record the forcings of climate, what caused climate to vary in the past. You can look at the tephra and the sulfate and look at the volcanic history, look at how climate responded to that. The anthropogenic greenhouse gases trapped in the bubbles, what was the natural variation in those through time, and what role did they play in climate? And so that makes them a very important archive on our planet. They are globally distributed, a lot of records out of Greenland and Antarctica, but also from the very highest mountain regions on the Earth. And there are parts of the world where we don't know very much about long-term climate variability. So they kind of fill in the picture. To do any research, you have to have laboratories. At Ohio State, we have over the years built clean rooms for the chemistry and the dust measurements, mass spectrometers for measuring the stable isotopes. You have to have storage facilities to keep that ice frozen when you get it. We have now over 7,000 meters of ice stored in this freezer at minus 30 degrees C. It's the only tropical collection on Earth. And as the glaciers disappear, this collection becomes more valuable. And we also design and build the drills for this work because it's high elevation. You can't use heavy drills that are, and energy supplies that are used in the polar regions. So you have to design those. So over the years, these are the places that our team has drilled. And you can see that we're getting a kind of a global picture recorded in the ice. And in the next couple years, these are the places we plan to drill. We just finished drilling Wakan a couple months ago, and our next program is down in the Antarctic Peninsula starting on December 14th. Here's an interesting one over in the center of the Warm Pool in New Guinea. We hope to drill there next May, June. I want to take you to one of these sites, to the Quelccaya ice cap in southern Andes approved, because we've studied that the longest period of time, but it's also the largest tropical ice cap on Earth. And so if you are approaching this ice cap, you can see it in the distance here, and it's in a remote part of the Andes, so getting equipment in and getting frozen ice core out is always a challenge. But it has a wonderful record. This is what an ice core looks like. This is in 2003. And we've continuously perfected the drills to get continuous ice core segments so that we can look at this record in great detail. If you look down into the Quelccaya ice cap, you can actually see every dry season. You can see these dust layers. And if you go down in the crevasse, you can see how horizontal these layers are. On many glaciers, you have reworking of surface snow, sastrugi, and through winds. And here, because of the extreme radiation in the morning, even in the wet season, the surface gets fused, so you don't have a lot of reworking. So you can actually measure the thickness of these layers and calculate how precipitation has changed through time. They're a wonderful archive, and I'm just going to show you a few of the parameters we measure. These are the isotope record that we use for proxy for temperature. These are the annual dust layers every dry season, and this is a period from 1805 to 1825. And as you go down the core, you can see the time gets compressed because ice is a viscous fluid. This is a period from 1520 to 1560. The Spanish arrived in this part of the world in 1531, so that's the first time we have written records from that part of the world. And if you go even deeper, here's 1240 to 1330. You can see time getting compressed, but you can still see every individual year recorded. The reproducibility in these records are remarkable. Back in 1983, when the first tropical ice core was drilled, we didn't have any refrigeration, any way to keep the core frozen. And so we had to cut it into 6,000 bottled, watered samples, sealed in wax, that we brought back, and Willie Dansgaard did the isotopes on them. And those are shown in blue here. These are annual values for the last 500 years. And then in 2003, we brought back frozen ice core so that we could keep it frozen until we got it to Ohio State, and we did the analysis. And you can see the reproducibility in these records. And that reproducibility is extremely important. So here are decadal averages for the last 1,000 years. This is the first core drilled back in 1983. This is the new cores from 2003 near where this was drilled, and 1 kilometer to the north on the North Dome. But you can see the little ice age in the isotope records, the warmer period before that. You can see the warming in the 20th century recorded in these cores. But you can also then look at what has happened to precipitation over that period of time in those same cores. And so here's a decadal record of net balance. Precipitation is measured in an ice core for the last 1,000 years. And you can see the similarity, the reproducibility that's in the record. And more importantly, if you look at the 20th century here, you can see that the 20th century has actually been above average in precipitation. And as I'm going to show you, this is the time that this ice cap has really been retreating and accelerating in the rate of retreat. There's been a lot of discussion about do isotopes tell you in the tropics. On the Quelccaya ice cap, because we can look at every year precipitation and the isotopes, you can actually look at 1,688 years comparing those two parameters. And when you do this, you see there's no relationship on the long term between the isotopes and temperature. And in fact, if you look at them through time, going back to 315 AD, you can see that there are periods when isotopes and precipitation are positively correlated and periods when they're negatively correlated, but overall there's no correlation over those long periods of time. If you look at what's driving the isotopes, this is a Quelccaya ice cap, and in 2003 we also drilled a new site, Corapuna, that is at 21,500 feet, right above the Pacific Ocean. But if you look at the isotopes in those records, what you see is whether you're looking at Quelccaya and you look at the sea surface temperatures starting from 1857 to 2003 on Quelccaya or Corapuna, what they're really capturing is SSTs in the tropical Pacific. And we think that's where a lot of the water vapor that is affecting the global water vapor budget comes from. And all the tropical glaciers have this same pattern. So they're really looking at SSTs in the tropical Pacific. This is a site that we just returned from between Wakan and Copa. If you look off to the west, this is the Pacific side. If you look off to the east, you're looking into the Amazon basin. And here we were able to recover the deepest cores drilled to date, core to bedrock, 195 meters from this site. And the cores have to be stored under the snow while you're drilling because you're up there for usually a month or 6 weeks. And then they have to be transported down to the freezers down below. So it's logistically, it takes a lot of people and a lot of effort for that to happen. In the tropics, one of the big factors, and when you look at precipitation, is El Nino or INSO oscillations. And if you look at Peru here, you can see that the northern part of Peru is wet. This is during the 1998 El Nino. And the southern part of Peru and Bolivia are dry. This is a characteristic of that part of the world. And we know that on the short term where we have meteorological records. But you can take the ice core records and you can actually look at, this is the net balance, the precipitation record here, blue being higher and brown being lower precipitation. And when you look at that record and you look at the rise and fall of civilizations before the Spanish arrived, what you find is that when it's wet on the Altiplano, you have the development of highland cultures. And that's the same thing that happens during La Nina in today's world on very short-term periods. And then when it's dry on the Altiplano over long periods of time, then those cultures disappear and you get coastal cultures developing, which suggests there's a longer-term oscillation in this system, perhaps that's related to overturning in the Pacific Ocean, but certainly related. Now, you can take these records and you can composite them from all over the tropics. So this is a composite of these records and these records from Tibet for the last 2,000 years. These are decadal isotope records. And when you look at this, you can see the medieval warm period in here, the Little Ice Age, and then what really stands out is the warming in the 20th century. You can compare this to other temperature reconstructions from the Northern Hemisphere based on paleo records. And you can see a very similar curve. And this is the instrumental record in red. And what really stands out in these records is the last 50 years. And now you can take this record and you could take it to the US Senate and show them an isotope curve. And you get this kind of this glazed over look in their eyes. And it's hard to bring the message home. But what they really do relate to is what's happening to the ice. And so I'm going to take you around the world and show you some photos of glaciers and kind of give an overview of what's happening to ice. So if you go up to the Brooks Range in Alaska, this is a photo of the McCall Glacier in 1958 and in 2003. In the Brooks Range, 100% of the glaciers today are retreating. If you go to southeast Alaska, there have been some very major changes. This is a photo from 1941, the Muir Glacier, and then in 2004. In southeast Alaska, 98% of the glaciers in today's world are retreating. If you go to the Himalayas, it's very hard to find old photos of glaciers. But this is a glacier position in 2002, debris-covered ice here. But this is where it was in 1957. And in this area, there are over 46,000 glaciers in the Himalayas and the Tibetan region. The Institute of Tibetan Plateau Research is actually studying 612 of those. Out of the 612, 95% have been retreating since 1980. But there's a lot of glaciers in that part of the world. If you go to the Alps, we have our oldest records from that part of the world. This is a photo from 1903. These are glaciers coming down. This is going to fade into 2005 to show the loss of ice in that part of the world. 99% of the glaciers in the Alps are retreating in today's world. Now, we spent a lot of time in this area in the tropics, between 30 north and 30 south. And as was pointed out in the introduction, this is where 50% of our planet's surface area actually exists. This is where the energy that drives the climate system comes into the planet, and therefore a very important place to understand what the natural variations of climate have been, but also because so many people live in this area. And one of the biggest factors here is the Hadley cell. And there's a lot of discussion in the literature of intensification of this cell. And over the last 20 years, it seems to be broadening. Have moved, the descending arms have moved 2 degrees north and also 2 degrees south, thought to be contributing to the increased droughts in Australia and in the American Southwest and in the Mediterranean. In the model projections, this system will intensify under a warmer world. But of interest to the glaciers is that you can see where the latent heat is being released. This is the millibar levels. The maximum latent heat release is right at the elevation of where these tropical glaciers are sitting. And I think that's why we see all of them retreating in this zone in today's world. If you look at the sea surface temperatures in the tropics, you can see in this central panel a lot of variability, and that precipitation is tied to those warmer temperatures. But when you get up into the mid-troposphere, where the glaciers set, temperatures are very uniform throughout the tropics. This is a characteristic of the tropics. And you can actually watch how heat is transferred up into the mid-troposphere during an El Nino period. These are months before a maximum El Nino, when you get the warm water off the coast of the Peru. And this is looking at heat moving up from 300 to from 1,000 millibars up to 300 millibars. And you can see within 6 months, that heat is transferred throughout the tropics around the world and encompasses all the sites where these tropical glaciers exist. There's been considerable work done now on the ice fields on Kilimanjaro. The oldest photo that we know of was taken in 1912. These are glaciers on the mountain. This is another photo from 1970. You can see a canyon here, and then by 2000, you can see how much ice has been lost. And the people who live there have watched the ice retreat up this mountain. One of the things we've been doing since we drilled in 2000 is photographing the glaciers, so looking at the changes that are taking place there. In 2000, this is the drill camp here. This is the northern ice field. You can see the drill dome. We drilled 3 cores to bedrock from the northern ice field. And the longest one of these records goes back 11,700 years. And if you look at that core, and you look at just the physical parameters in the core, the lower 49 meters of this 50-meter core looks like this. This is normal ice when you have snow that becomes firn, that becomes glacier ice. But on the top 65 centimeters shown here, you see these elongated bubbles. These form only when you have melting and refreezing taking place. And had that condition occurred in the history of 11,700 years, you should physically be able to see it in the ice, and we don't. And that suggests that what's going on the mountain today is different, at least in that time period. We've continued to monitor that and been working with Doug Hardy, who's here in the audience, looking at the changes on the mountain. This is a Furtwanger Glacier in the crater. This is what it looked like in February of 2000. This is what it looked like by 2006. You can see the bedrock being exposed as this hole develops. And then by 2007, the glacier has totally separated. And as you expose more of the darker surface, you absorb more energy, you get more loss of ice, and this is occurring on the glaciers on this mountain. On the Furtwanger Glacier, where we drilled, we actually put in an accumulation stake that goes right to bedrock. The lower 4.67 meters is actually drill extension, and then the top 6 meters plus was bamboo. And we put this in 2000. This is what it looked like in 2004. And then Doug Hardy was over there in February of 2009. And if you look at the photos that he took, you can actually see the top of the drill stem now being exposed as this glacier is thinning from the top down. So since 2000, we have lost the upper half of this ice. Between February 2000, February 2009, 4.83 meters of solid ice was lost from the surface down. That's about 50% of the thickness of that glacier. And if you look at the rate of ice loss, that's averages about 0.54 meters per year, and which would suggest that glacier will disappear sometime before 2018. And the thing that's deceiving when you're just looking at an aerial photograph is that you're looking at only the area, and you don't get the sense that these glaciers are actually losing mass, and that actually, and we know now that 50% of the mass loss is actually in the thinning of these glaciers. So it's very important. This is what the Furtwanger looked like in April of this year. And you can see the division here, and it's starting to break up into even smaller pieces. A lot of discussion of whether there's any melting on Kilimanjaro. Well, when we drilled in 2000, this is water coming out of the drill. The Furtwanger Glacier was totally water saturated at that time. So if you look at what's happened to the ice, back in 1912 there was 12.1 square kilometers. In 2007 that's down to about 1.85 square kilometers. So we've lost 85% of the ice on the mountain. And if you kind of connect the dots of all the maps that have been made and projected out in the future, in the next few decades, we will lose the glaciers on Kilimanjaro. Now, Doug's taken some really nice pictures of, this is a little pink glacier in 2000. There's been a lot of discussion that maybe the flank glaciers are behaving differently than the glaciers up on the crater. But this is a flank glacier in 2000. And here's a quote from one of the papers: distinctly convex shape, e.g. like this little pink glacier, which indicates that these glaciers are close to equilibrium. Well, this is what it looked like in 2000, and this is what it looked like in 2008, having lost 40% of its area. So these flank glaciers are behaving very similar to what's happening on the summit of the mountain. So here's kind of the summary. 85% of the ice that covered the mountain in 1912 has been lost by 2007. 26% of the ice that was there in 2000 is now gone. A radioactive signal marking the 1951-58 Ivy test, which we found in 2000 at the top of this very long core we use for a time marker, was 1.6 meters below the surface. By 2007, we had lost 2.5 meters of ice at that drill site, so that layer is now gone. The presence of these elongated bubbles say that the conditions that are existing at the top of the glacier in today's world is different, at least in that 11,700 year perspective. Ice volume changes from 2000 to 2007 calculated for the two ice fields reveal that nearly equal ice volumes are now being lost to thinning and to lateral shrinking of the ice masses. And finally, Kilimanjaro ice loss is contemporaneous with widespread glacier loss in mid to low latitudes around the world. So it's not unusual what's happening on that mountain. Now we've spent 25 years working in China, and these are the places that we've drilled with our Chinese colleagues from the Institute of Tibetan Plateau Research. And it's a very important part of the world to understand what's happening to glaciers because of their impact on water supplies. If you look at the major rivers that source out of this region, you can see them here. There are some 12,000 cubic kilometers of fresh water tied up in these glaciers, and there are some 15,000 just in the Himalayas alone. And they're very important for water supplies for people. And I'm going to take you to this most recent site, which we drilled in 2006, Nanunami, which is at the source of the Ganges, the Brahmaputra River, which flows along the northern flanks of the Himalayas, and the Indus River. And this is the mountain. It's a beautiful place. And if you make your way up through these canyons, you come to the Nanunami Glacier, and then up to the top is a very flat plain. And so we drilled 3 cores to bedrock here. The deepest is 158 meters. You can see the drill camp out here. So it's a massive ice body. And we use these lightweight drill systems to recover those cores. And the cores, when you drill them, if you're drilling in a place where people have never drilled, you can actually see very abrupt changes that have occurred in the distant past while you're drilling. So drilling is kind of an exciting process because you never know what the core is going to bring up. But here we use Sherpas to move the cores down to the edge of the ice. But unlike the Andes, when you get to the edge of the ice, you're still about 4,000 feet above where vehicles can come down below. So we have to go to local transport system. These are yaks, and these are insulated core boxes. And you can get 6 meters to a box, 12 meters per yak. We drill 500 to 600 meters of core. So what you end up is a herd of yaks that you have to get down to where the vehicles are. And the first thing we do when we bring the cores back is that we look for all the thermonuclear bomb tests that man has done in the atmosphere. These are marker horizons for us. We know exactly when and where these tests took place. These are all the previous glaciers we drilled in China. And you can see the 62, 63 Soviet test, which gives us a very fine time marker in these remote areas. We look for it in Nanunami, and it's not there. Then the next thing we looked for was the Ivy test. Since the Ivy test was done at sea level, there's chlorine-36 produced in those explosions, and that goes global. And you can see it in all these glaciers. You can see where it was on Kilimanjaro back in 2000. That would now be gone because we're losing the mass from the surface down. And this is Nanunami, and it's not there. And that means there has been no net accumulation on this ice field since at least 1950. And this is right at the source of these major rivers. So I think these changes are coming fast. The problem with that is that's one site in the Himalayas, and so you're trying to talk about what's happening to all the glaciers, all 46,300 of them, and that's very hard to get a handle on. But here's some GRACE gravity recovery and climate experiment data, which shows glaciers over in the Palmiers, showing that the surface lowering that they're seeing taking place. And then here's one in the eastern Himalayas that would tend to confirm that we're losing mass from the surface down. The problem with this type of analysis, you can see where the glaciers are, and the footprint is about 200 square kilometers. And we know that these surfaces are lowering, but these glaciers aren't that big. And so you really need ground truth to understand exactly what's happening. Now, if you go down into the Andes of South America, you find a very similar story in the tropics. These are some of the places that we have drilled. And if we go back to the Quelccaya ice cap, this is now the longest documented retreat story in the tropics. And this is something we decided to do when I was a graduate student, not to look for any evidence for warming of the Earth, but just to see how a glacier flows in the tropics. And so this was the first photo back in 1978. This goes up to 2006. This shows the actual retreat of the glacier up this valley and the formation of the lake. And this shows that it's actually been increasing the rate of retreat exponentially since we've been measuring it. So in the first 15 years, this glacier is moving up the valley about 6 meters per year. In the last 15 years, it's over 60 meters per year. That's about 1.3 feet per day. So you can almost sit there and watch this thing retreat. And the whole ice cap is behaving in the same way. This is a photo from 1977 of a boulder. It's a very large boulder that's being pushed by the ice. This is the same boulder in 2006. You're looking at the end of it. You can see the lake that's formed. And if you were up on the ridge back in 1978, you can actually see the boulder here, and you can see the ice that's setting in here. And if you look at the same place in 2006, you can't even, you can just see the edge of the ice down here. And over that period of time, since I was a graduate student, we've lost 25% of the area of the world's largest tropical ice cap. So these changes are coming very rapidly, and of course that water is making its way into the world's oceans. Now the question is, what's driving these changes? And if you look at this image, this is a transect from north-south in the Rockies that Ray Bradley actually put this together. And these are mountain peaks. And then these are the sites where we've actually recovered ice cores. And if you look at that projection of 3-degree warming by 2100, that's surface. But if you look at the vertical, you can see that warming is much greater at high elevations in the tropics, actually double. And we think these glaciers are already starting to see that. You can look at the isotope records from the cores in Tibet. This is the lowest elevation core that we've drilled to date, 5,325 meters. These are higher and higher elevation. This is the highest at 7,200 meters at 23,500 feet. And if you look at the isotopic enrichment since 1950, you can see it's much higher at the highest elevation sites, which would be consistent with the projections for this part of the world. If you look at the loss of ice, the retreat of glaciers, this is the percent of ice loss, the measurements that we have, you can see that it's accelerating, whether you're talking about the Himalayas, Kilimanjaro in Africa, or Corycalis down in the Andes, Peru. Again, suggesting there's something that ties these sites together. Now, if you're skeptical on climate change, you're going to say, well, wait a minute. These photographs, you know, we haven't had photography that long, and how do you know that this hasn't happened in the past, and how do you verify that? Sometimes you can be lucky and find an older photograph. This is from the 1930s. Chambi was a Peruvian photographer. We went back to the same site in 2006, and you can overlap these images. And the white areas are where the glaciers are today. The gray areas are where the ice has disappeared. And you can see it's not just retreating up the valley. These glaciers are thinning from the top down. But still, that's not very long. And the question is, well, can you give a longer time perspective? And the answer is, yes, you can. And this is a quote from Sir Ernest Shackleton: "What the ice gets, the ice keeps." Now, he was talking about his ship, the Endurance. But it's true about ice. Anything that ice gets, it keeps. And as these glaciers retreat, things are coming out. And these things can be collected, and they be carbon dated, and you can actually reconstruct what those changes have been. So if you go back to this Quelccaya ice cap, back when I was a graduate student, here we are going up this on the ice field. This is all now a lake in here. And this was the backside of that lake in 2002. You can see a person for scale. It's about a 30-meter high wall. We found a wetland plant deposit rooted in growth position, just coming out as this ice wall was retreating. If you look at the 2002 photo, here's the plant, here's the ice wall. And to give you an idea of how fast these changes are taking place, the next photo was taken in 2005. Here's the plants, and here's the ice wall in the distance. And many plants have come out now. We now have 60 that we've collected as this ice retreats, and we just collected 14 a couple months ago. And these plants can be identified, Stichia muscoides, and they can be carbon dated. And they can be compared to plants that are growing in the valleys below today. So this plant is 5,200 years in age, and perfectly preserved, and Cornell has just succeeded in reproducing DNA from these plants. And so that they're amazingly well preserved. Now you can look at other recorders in this area. This is Quelccaya in the distance. This is a lake that was drilled by Don Rodbell, and he has a record that goes back 14,000 years, and that's shown here. This is organic carbon, magnetic susceptibility, and glacier flour. And you can see 5,000 years ago, suddenly we get an input of glacial flow, and that means the glacier has advanced down the valley near the lake, and we're starting getting material coming in. But you can see how abrupt this is. In fact, we had with us this year National Geographic that was doing a special on 2012. You know, there's a movie out called 2012, but these plants were captured at the time that the Mayan calendar formed. And so they came to film that. And, you know, what do we really know about 5,200 years ago? But it's interesting when you start, I never thought about this until 2002 when we found the plants. But since then, we've been looking around at other things that have come out of the ice. Let's see, the Iceman came out in 1991 out of a glacier in the Austrian Alps. He is also about 5,200 years in age, and they know a lot about him. They know he was shot in the back with an arrow, escaped his captors, sat down behind a boulder at the top of the Eastern Alps, and bled to death. And we know that soon after he died, there had to be an event, a snow event, that was big enough to bury him and keep him buried for 5,000 years. Otherwise, he would have decayed or he'd been eaten by bears in this area. And so you can look around at other things. Lake Tahoe. In the southern end of Lake Tahoe, there are trees buried under the water. And these trees have been radiocarbon dated. And these trees started drowning about 5,300 years ago when lake levels rose. But for these trees to have been preserved for 5,000 years, the water in the lake has had to stay high for the last 5,000 years. And so you can see that this is a large-scale event that occurred back at this period of time. In fact, you can look at all kind of paleo records. Here's a speleothem record from southern Israel. There's only one event in the last 12,000 years, 5,200 years ago, uranium-thorium dated. These are ice core records of methane from both Antarctica and Greenland. The lowest methane level in the Holocene is 5,200 years ago in both hemispheres. This is the isotope record from Kilimanjaro. The biggest event in that record is 5,200 years ago. And we know down in South America, many of the proxy records show the onset of El Niños occurring at this time. So it suggests a natural, abrupt change occurring back at this time. And in fact, this event is recorded in many records around the world. So 5,200 years ago, there may have been 200 million of us on the planet, not 6.8 billion that we have today. So it's an event that we should probably try to understand what were the causes behind it. And then to come to modern times, you say, well, would we recognize an abrupt climate event if it was happening? So here's a couple photos. This is from the Northwest Passage in August of 2006, the first time that it was ice-free. This is Lake Mead in the American Southwest, where the water levels are only 50% of what they should be. This is the Coriolanus Glacier in 1978. This is what it looked like just a couple months ago. And you can see the ice is now completely out of the lake. So the retreat continues. And then when you put this in the bigger picture of what's happening in the polar regions, the breakup of these ice shelves, and it's really interesting when you look at the dates on these, and you go back and you read a paper that John Mercer wrote in Nature back in 1978. In his concluding paragraph, he said the first evidence for global warming due to increased CO2 in the Earth's atmosphere will be the breakup of the ice shelves in the Antarctic Peninsula. And they will start in the north and they will move to the south. Now he passed away many years ago, but it's amazing that he foresaw this happening. We know that the ice shelves are floating, therefore their breakup does not cause sea level to rise. But we also know that when we monitor the glaciers flowing from land into the ocean, that the rate at which they're flowing has accelerated significantly with the loss of those ice shelves. And if you go further south, where we still have an ice shelf, then you don't see that acceleration taking place. Very important to recognize that the Intergovernmental Panel on Climate Change did not project increased rates, the physical response of glaciers to warming, this rapid flow that's been monitored or seen in the last few decades. You've all probably heard of the sea ice up in the Arctic, and this is the record coming up through 2008. some huge variations from year to year, but losing about 11.2% per decade. The increase in the number of melt lakes in the southern part of Greenland and in the margin areas of Greenland. These are crevasses underneath the ice. Water finds its way through moulins, gets down and apparently lubricates the bottom of the glacier, such that many of these outlet glaciers have increased their flow rates 20 to 100% in the last 10 years. And so if you look at sea level, what do we know about sea level changes? For most of the 20th century, sea level was rising at about 2 millimeters per year. And that the contributors were mainly the expansion of the oceans as they warm. Alpine glacier mass loss contributing about 30% of that rise. Ice sheet mass loss to big Greenland and Antarctica, about 10 to 20%. And pumping groundwater, more groundwater than is going back into these archives, all contribute to sea level rise. And currently, about 60% of the land-based ice loss comes from small glaciers and ice caps. I think in the next 20 to 30 years, the most important loss of ice on the planet will come from the mountain glaciers because they're small and they respond very rapidly to change. And the fact is, we don't know how much water is tied up in the mountain glaciers on the planet. We have estimates, but we don't really know. Since 1990, sea level has been rising at about 3.3 millimeters per year. And in the last decade, many of the glaciers draining Greenland and in West Antarctica have accelerated their discharge into the oceans, 20 to 100%. This is highly variable, and we don't have long histories of that variation. But how they behave in the future will be very important to what happens to sea level. But I think it's often very good to just step back and say, okay, what do we really know? All the red areas on this map show places where we're losing ice on the planet in the 20th century and the beginning of the 21st century. So climatologically, we're in unfamiliar territory, and the world's ice cover is responding to this change. Now, you can look at this and you can say, well, you know, what if we were really conservative? And you say, what if we only lose 8% of the ice that's now on land? How would that change sea level? It's important to point out that Kelkaya, since I was a graduate student, has lost 25% of its area. So I don't think it's an unreasonable thought. So you can take the coastal areas, the Gulf areas of the US, Florida, and you can look, if you lose 8% of the ice on land, what would it look like? So here we are today, lose 8%, that's what it looks like. If you go to New York or any city that's on the coastal area, you can look at the changes. This is today, lose 8% of the ice on land, this is what it would look like. And so the real impact here is in all the infrastructure that we have built in these coastal areas. So I think when you think about society and what our options are, we have only about three. One is prevention, and that means taking measures to reduce the pace and the magnitude of climate change in a global climate that are caused by human activities. And those are examples are the reducing the emissions of greenhouse gases, or enhancing the sinks, or you can think about geoengineering, what you might do to counteract the warming effects of these gases. There's adaptation, which means taking measures to reduce the adverse impacts on human well-being that result from the climate changes that do occur. We already have built in a significant climate change going forward, even if we started reducing our emissions tomorrow. And examples of this is changing agricultural practices, strengthening our defense against climate-related diseases, building more dams and dikes, but this is a moving target, and we don't know regionally how things are going to be impacted. And then finally is suffering. That is the adverse impacts that are not avoided by either mitigation or adaptation. And the history of human beings would say, we know who suffers. It's usually those who are least prepared, have least resources, and in this case, probably least responsible for those changes. This is a Quechua Indian girl who lives just below the Kelkaya ice cap down in the Andes in Peru. So here are some of the key points made in this presentation. 20th century is the warmest in the last 2,000 years, as recorded in low-latitude ice cores, and in several places it's the warmest it's been in at least 5,000 years. Glacier loss on Kilimanjaro and Kelkaya continues unabated in 2009. The recent documented mass loss from Kilimanjaro in Africa and the Anunnaki in the Himalayas is disturbing, given the projected 21st century warming for high elevation sites in low latitudes. Climatologically, we're in unfamiliar territory, and the world's ice cover is responding dramatically to those changes. The observed rapid changes in Greenland and Antarctica are not predicted by our climate models. They have assumed a slow and linear response to climate forcing, not the fast glacier flow we're now observing on many glaciers. Glaciers in most parts of the world are rapidly melting, and their loss will impact 2 to 3 billion people, either through water resources or through sea level rise. And a valuable paleoclimate archive will be lost forever. The problem with losing the glaciers is once they melt, that history is gone, and you will never recover that, even if the climate gets cold and you start rebuilding them. What's there will be gone. And finally, glaciers are our most visible evidence for global warming. They integrate many of the climate variables in the Earth system. Their loss is readily apparent, and they have no political agenda. And so just a couple closing slides. One thing we know is our planet is unusual. If we've learned anything from all of our exploring of space, and it's very unique for supporting the life forms that, as we know them. But the other thing, when we talk about global warming, the fact is that nature is the timekeeper, and unfortunately none of us can see the clock at which we're working, and whether abrupt changes are in the future in that climate system. And then I'd like to close with a quote. There are 3 stages in scientific discovery. First, people deny that it's true. Then they deny that it's important. And finally, they credit the wrong person. The interesting thing about this quote is it comes from Alexander von Humboldt over 150 years ago. So human nature really hasn't changed that much. So with that, I'd like to close, and thank you very much for your attention.
I understand that the Ohio chapter of professional geologists has recently issued a statement about that climate science is still pretty hazy. I'm just wondering, I mean, do they know that you're from Ohio, and have you gotten involved in that?
No, this is an issue that's been with us, and the fact is that we have a flat Earth society that's live and well, and even in the face of all the facts, some people will not change. I try to look at people, the human race, as something like a normal distribution. You got wings on both sides. You can't reach these people. There's 80% in between that will listen to reason and what's out there. And I think that's the best you can do, is to present that to those people. No, I fully understand. If you've not seen it, there's a whole non-governmental panel on climate change report that's out, that's supposed to counter the IPCC report. And but it's, all you have to do is to look at the science. And ultimately, this is most important: is science has to go through peer review. It's got to be things that your peers and your colleagues can look at, check, and validate that what you're saying is true. And a lot of most of this stuff doesn't go through peer review. And but unfortunately, in today's world, with the internet and blog sites, this stuff goes global before anyone bothered to check the facts. Excellent case right now in AAAS in science. There's a story about glaciers advancing in the Himalayas, based on a white paper that was produced by the Minister of the Environment in India, and based on looking at 25 glaciers. And if you read the report, there is no science in this report. And what science there is would suggest that the glaciers are retreating and has nothing to do with the conclusions that that report came to. And so there's been a huge controversy going back and forth. But the fact is, since it was a white paper, it was never meant to be considered as a scientific report, and in my opinion, should have never been published in Science for that very reason. It just doesn't show quality control. No, it's a big issue. Yeah.
I was wondering if you have any advice about communicating our science effectively to lay people about climate change. I really appreciated the manner in which you dealt with it, and so for us as an audience, advice or thoughts on how to do that effectively without depressing people too much?
Yeah, I think it's very important. If you're a scientist, you got to stick with what you know, or at least what you think you know about the records that you're looking at. And we've made it a real effort to, when we go to Washington, it doesn't matter whether it's a Republican or a Democrat that invites us. We'll go and we present, as the world as we see it. And I think that it's very clear that on both sides of this issue, there are people who are very concerned. Senator McCain is very concerned about climate change, and he had this is very telling to me. He had a group of insurance people and scientists come about a year and a half ago, and they had a CEO from Swiss Re, which was it's the biggest insurance company in the world, and the guy, the insurance companies did their presentation of losses due to storm-related events around the world. And you look at those curves, and I think some of our curves look really bad, but those were even worse. But the thing that really struck me is this CEO from Swiss Re said that had Katrina hit the United States in 2001 rather than 2005, it would have brought down the global insurance business. And the reason for this is that they were reeling from the tech crash in 2000 and the terrorist acts in 2001. And you sat back and you think about it, well, in reality, there's no reason why Katrina could not have hit in 2001. And sometimes it's just a nexus of events that makes something, turns it into a crisis. And so my feeling is that it's very important to communicate the science, and at the end of the day, as a scientist, you should just stand with the numbers, and the criticism that comes, okay, fine, if you want to believe that. But at the end of the day, I believe what is what we all will have to deal with, and the changes that we've seen are very, I think, scary in many ways. Because if you think about ice, I mean, you think about glaciers. I mean, you used to comment, my administrators at Ohio State, I'd say, they're moving at the rate of a glacier, and that meant something very slow. And now it's no longer true. These glaciers respond very, very, very rapidly. But I think it's very important to get out and communicate. I mean, get the facts, but then go communicate them to your policymakers. But it's up to them to then take that information and come up with a proper policy that we need to deal with these issues. Yes.
I'm interested to see if you have any thoughts on how to communicate all of these ideas that you've been talking about to poor communities that usually don't have the infrastructure, and in many cases they're more concerned with other things, such as just getting like a basic livelihood. Yeah,
survival. Well, this is I showed that picture of the lights at night. The fact is, right now we have 1,600 million people on this planet that do not have electricity, even in today's world, and therefore they have no access to internet or that type of communication. So it's a real challenge. Going beyond the one-on-one type of interaction. We make an attempt with our programs to produce our records in the language in where we're working so that it's better disseminated. And then we also give lectures like in Peru, where sometimes we'll have a Spanish translator and a Quechua translator, and that way we can have at least some communication taking place. But it's very, very difficult. I think mass media, if you can tune it right, you know, a lot of people get all their information from television. And you can say that's really horrible, and it is, but it's truth. And therefore, you have to somehow communicate with those people through those means. But sometimes I think in today's world we have more means for communication. TV, I mean, if you have, most of you, if you have a TV, you probably have 100 channels. And you can hear anything you want. And same way with all the media. So I think people who are prone to look at the world in a certain way watch the things where they talk like they do and believe like they do. And so we got lots of ways to communicate, but we're not really communicating. It's not the idea that you're looking at two possibilities and coming to some compromise. I think there's less communication now than there was probably 50 years ago for this reason.
We spent several months in Peru 35 years ago. We were just there again several months last year. The people in Lima on the coast where it doesn't rain were concerned about their water resources longer term. What's the water table doing there?
Well, Peru is a special case, and that's why we've spent so much time there. First of all, they have 70% of the world's tropical glaciers. And they have 80% of their population living in that western coastal desert, depending on rivers that originate from the Andes and from, in many cases, from glaciers. 76% of their electric power comes from hydro, and all those are at risk now, especially in the dry season as water levels drop. In Lima, that's where 55% of the population lives in Peru, out in the coastal desert. They have one river, the Rio Mac, and they are looking at tunneling through the Andes to capture rivers that are now flowing into the Amazon and bring that water back to the west coast. But those are expensive undertakings for a relatively poor country like Peru. So I think the water tables are being diminished, just like they are in India and here in the U.S., China. I mean, it's when you look at the rate at which groundwaters are dropping in these areas that produce their food supply, you have to wonder, you know, how long is this sustainable? It doesn't make sense. But Peru is particularly vulnerable to climate change.
I've been to quite a few lectures on climate change, and one of the things I'm seeing that's missing is even a basic high school explanation of how a greenhouse gas molecule will cause global warming. And I've surveyed quite a few of my friends, people that are knowledgeable about climate change, and even a lot of them cannot explain how a molecule of greenhouse gas is going to relate to cause global warming. And so I think that that's an important part when it comes to people believing that climate change is secondary to greenhouse gases. And so with only, I think, 37% of Americans actually believing that it's based on human activities, it's important to explain to them how the basic science and even high school terms, you know, exists.
I would agree with that, and especially when you go talk to your congressmen and your senators. It's amazing to me that I don't think many of them have had a science class, and you know, and they're making decisions on things that, you know, they somehow, as in the educational system, we have failed in not exposing these people to basic science, and that's something we need to work on. My fear is that we may not have as much time to educate as we need. I'm very encouraged by the younger generation because in our discussions earlier here, at Dartmouth, but at Ohio State, the number of people who are really, young people, who are really concerned about their environment and more importantly, what they can do to change the future. And I think that's step number one. So I agree totally with what you're saying.
In one of my classes, we were doing a lot of reading about climate change, and everything that needs to be happening isn't happening, it seems like, because it's not cost effective and it's not meeting the bottom line within industry. Is there any way that you see that the United States or even globally we can overcome that?
I think you've hit on the real problem here, is that if there was a solution that made economic sense, it would be adopted overnight globally. And to make an indication of that, all you have to do is think about the cell phone. How many of you have cell phones? Yeah, you go to China, they have more cell phones. And you know, this is technology that came out in 1991. And in China, they have totally bypassed landlines and all the resources that would be required to put that in to embrace this new technology, because it made sense, made economic sense. And if we could do the same with energy, I think these things can change overnight. So it's a very, very important point.
Meredith, let's give Meredith the last question. And if you have more, come forward. I'm sure Lonnie will be happy to.
Hi, Lonnie.
Hi, Meredith.
One aspect of global warming and mountain glacier retreat that you touched on but didn't go into is the formation of these lakes in front of the glaciers. And potentially those lakes are really unstable and are located at high elevations above villages or above cities and can be really dangerous. And I was just at a conference last week about glaciers and climate, and there was an engineer there who said that in Central Asia there were 2,400 of these lakes that had formed that were considered extremely dangerous. And I was wondering if you could comment on that, if you're contributing any data in terms of ice recession to studies of those lakes.
Well, I think that's a new geologic hazard that is developing as these glaciers retreat. And as you know, on Kilkaya, there where we camped since I was a graduate student, we were camping right in the middle of the glacier because there's a stream, a continuous water source. And that stream got bigger and bigger. And then when we went down in 2005, it was gone. There was no water coming down. And when we went up to the lake that fed it, that whole lake was gone. It was now, all that water was flowing into another valley to the south. And the valley that it had been flowing in, all the alpaca moss had dried up. They couldn't feed any of their animals there. And the other valley is flooded because it has more water than normal. So these changes are certainly taking place. And these mud flows over in the Himalayas, where you get these bursts of these glacier lakes, are real hazards. And I think, at least on the north side, in the last 20 years, there have been 50 of these bursts that really impacted people downstream. So in any mountain region where you have these very high perched lakes, it's a problem. And I know Electra Peru, before it was privatized, they had a project draining a lot of these high elevation lakes because of the risk to cities that were down in the valleys below them. But now that they're privatized, they don't do things like that. Yeah.
I should point out, Meredith's one of the many young scientists that have been in the field with Lonnie and have gone on to do their own work in places like Peru and high elevations. So Lonnie, I want to thank you very much for a wonderful presentation.
Thank you. Thank you very much.